Wait class, wait. Okay. Share my screen. So this is the sample problem. I hope you can see it. I'm doing the slideshow. I'm sharing it. That way it would be bigger. Uh, in this sample problem, you're given pure gaseous reactant A. So the keywords that you're going to take note of in here are these two: gaseous, and this one, very important also, pure. Gaseous reactant A. So this is the initial concentration of A. It's fed at steady state to a mixed flow reactor, and this is your stoichiometric equation. And these are the series of runs at different volumetric flow rates. That way, we can measure the remaining amount of A, or the unreacted amount of A, for these different volumetric flow rates. The goal is, using this series of runs, you'll be able to tell the rate equation for this reaction. So the keywords that you're going to take note of in here, because they're both very important, is that if the reaction is gaseous, it is gaseous, automatically your epsilon A will not be equal to 0, meaning it's not a constant density system. Your fractional change in the volume will not be 0 because your reaction is gaseous. Now, another phrase that you should take note of, that way you will not miss in determining the epsilon A, is phrases like constant pressure. So it may not say that you have a gaseous reaction, but it will say that the reaction is facilitated at constant temperature, constant pressure. So constant pressure means that your reaction is also varying volume. So if that is the case, you have to consider again your epsilon A. So in this case, our first solution to this problem, which we did last meeting, is we failed to determine the epsilon A for this particular problem. Now, so that we will not forget, so before we start solving anything else, we have to write that epsilon A is not equal to 0, and we have to determine it right away. That way, we will not miss it in all our succeeding computations. Okay? Now, I clear my markings here, and let's go to the Jamboard. So we have a Jamboard for this. Let me just open the Jamboard. My files are still loading. We'll check which one in here is our solution. Then let's check. Okay. So I will now share a new screen. Let me check. And this is it. Okay, this is our second sample problem. Okay, you have pure A. So it was not indicated here. So we'll write here that you're given, sorry, you're given initially pure A. So we need to place it here right away that it's pure A, because it has a role to play when we determine the fractional change in the volume. So right away here in the given, we can write that epsilon A is not equal to 0. So meaning our reaction is varying volume reaction. Okay? Now in our solution, this is our solution, and this is the original formula that we used in determining the tau. Now we will use a different formula this time because we need to consider the linear relationship between conversion and changes in the volume. So I will clear the frame here. Okay, so we'll have a new solution for this one. So before we do any computation, since we already indicated that our system is not constant density, we right away determine the fractional change in the volume. Excuse me, please. So this is the volume at 100% conversion minus the volume at 0% conversion over the volume at 0% conversion. Okay? Now, anybody here who can tell me how we are going to determine the fractional change in the volume for this system, which starts with pure A? So I wrote the very important word pure A. It started with pure A. Now, anybody who can suggest how we determine the fractional change in the volume if we start with pure A for this varying volume system? Albert Villarosa, can you tell the class how we determine epsilon A? John Albert. John Albert, are you there? Can you hear me? How do we, yeah, okay, so there's somebody wrote in the chat box. So stoichiometry. Okay, so if it's based in stoichiometry, that is correct, Albert, then how are we going to determine our fractional change in the volume? This is your stoichiometric equation. 2A forming 1 mole of R. So how do we determine epsilon A, Albert? Or can I ask for via? So Mr. Albert already answered 1 minus 2 over 2. Very good. So this is how we determine the fractional change in the volume. 1 for the stoichiometric coefficient of the product minus 2, the stoichiometric coefficient of the reactant divided by 2. So this will give us negative 1/2 or negative 0.5. Okay, so that's our epsilon A. And anyways, we have here our set of information already. So we're given volumetric flow rates against concentration. Now, how are we supposed to determine our, or shall I say, that's the question, what would be the next step that we're going to do? So we already have the epsilon A. How do we, or what do we do next? Remember that if you're after RA, so I'll write here, if you're after RA, you need to determine the K and you need to determine the N. So these two, the K and the N, needs to be determined. Now, how do we determine the K and the N? Anybody who can suggest what should be the thing that we're going to do? This reaction is facilitated in a mixed flow reactor. What do you think are we going to do? It's there already. I already underlined the K and the N that we need to determine. So if we need to determine these two, what is the next step that you will do based on this equation? That way you can find the K and the N. Ezra, what do you think would be the next step that we're going to do? Ezra? I need the K and the N. So how do we look for CA? Okay. Ezra, you're going to look for CA. And I'll go back to our given information. So this is our given information. Do you know already CA or not? You already know CA because it's already given here. So there's no need for you to look for it. Okay, you are already given CA. Now, what do you think would be the appropriate thing to do next? Since you already have the CA. Okay, I asked Drexel. What do you think is the next step that we're going to do? You already have the CA. Drexel, are you there? Oh, sorry. This is our problem. We need to find the K and the N. Varying volume. So how do we find the K and the N? Josh said that we're going to find the CA. The CA is already part of the given. Okay? It's already part of the given. Then what do we do if it's already part of the given? How soon can you forget? We have only discussed this the week before the exam. What do? We need to solve for the Amit, Ezra. Look, in both sides. What do you mean, Patrick? In both sides. What do you mean, Patrick, in both sides? We're almost done with the first 30 minutes of the class. Ang RA na equation is, what do we do with the RA equation? Can I ask for help from Drexel? Are you there? Drexel is not.
Natural logarithm is of both sides.
Oh, if you're going to get the natural log of both sides, Iho, you're going to get the natural log of both sides, you need the value of RA, right? Since you already you have already the value of CA. So my question is, if you're going to get the ln of both sides, that's our procedure last meeting, you don't have the RA. Although if that is the next step that you want to suggest, so we can write in here. So you have ln of the rate is equal to the ln of the K plus the n ln of CA. I'll use a different color here so you would see. So far, you'll be able to get this one, this, and this if and only if you have the CA and this, but you don't have this, right? So that's actually what I'm asking for. Anyway, I point out to you what you're going to determine. So we need to determine the RA. How are we going to find the RA? Anybody can suggest to me a formula, an equation that we can use. That way we can find the RA. Correct, Dexel. That's what I mean. That's what I'm asking from you a while ago. The next step would be for you to write the performance equation of a mixed flow reactor, or that is your CSTR. Okay, so I'll close this one. We'll go to the next frame. So I will clear this one. Okay, we'll go back to my. Now, if it's the performance equation of the mixed flow reactor, can somebody dictate to me, the one who has the phone there, so that we can save time? What's the performance equation of a mixed flow reactor? Performance equation of a mixed flow reactor. Can I ask for Via? What's the performance equation of the mixed flow reactor? Okay, the performance Equation for the mixed flow reactor is tau, or that's your V over V sub O. The small v sub O is equal to CaO XA over the rate, right? So that we can save time and interchange these two since this is my goal. So I will have the rate equal to CaO XA over the tau. So let's see in terms of our given if we can solve for the tau already. So you have a different tau depending on the volumetric flow rates that are being used. Okay, so we'll have this formula here written in which you have the B and the V sub O. So since this is B over V sub O, I'll write this one now as CaO XA times the small v sub O over the V. Okay, your V is fixed at 0.1 liter. So it's true for all the runs that you will have 0.1 liter for the V. Now, what is going to vary in here is what's going to vary in here? In this equation, what's going to vary? Ano ang galain-lain sa sining equation ni hindi fixed? This one, the V sub O, and the conversion. That is what is written here. CaOXA and VO. Correct, Jericho. Very good. And Via, you have CaOXA. So both your V sub O, the volumetric flow rate, and the XA varies. So meaning for each of your runs, in order for you to find the RA, you need to find this as well, these two. But since our equation already have the V sub O and you already have the V, you need to determine first the XA. Now, what's our formula here for the CA at any particular time when you have already XA? Can you remember the formula for C sub A when we already have the epsilon A to consider? CA is equal to CA 1 minus XA all over 1 plus epsilon A XA. Right? Sorry. CA and this is CaO here. Now, from in here, you can solve for the XA at any particular run. So, in this case, you will have, we'll have a different table. I'll construct a table. I'll have here the XA for each runs. I have here the V sub O. And I have here, oh sorry, not the V sub O. I'll have here the rate. And I have here the C sub A. So I need to find the XA. That way I can find the rate. And then of course the CA I will just copy. So in terms of the CA, we already have it in the problem. So you have 85.7, 66.7. So we'll write it here. By 50 and 33.4. Okay, now we determine the XA. Okay, we determine the XA. How do we determine the XA? So you will have CA times the quantity 1 plus epsilon A XA all over CaO 1 minus XA. You can, wait it should be on the other side. And we can simplify. Actually, we have a ready-made formula for this. Nonetheless, I'll show to you the derivation. Meaning, what I mean is the formula for the XA. So you'll have here CaO minus CaO XA. On the left side class, you have Ca plus Ca epsilon A XA, and you have here Ca minus Ca XA. Now I'll keep these two in this side and I'll transfer, by the way, this is CAO. And I'll transfer this one in here. This one in here and in here. So I'll have, I need to write it in here. So I'll have, if I will factor out XA on the left side, after transferring this one, what I'll have is CA epsilon A for this one. And this one, if transferred here, will be plus CAO. Equal to what you have here on the right is CAO and this one minus CA. So I have now the formula which was shared to you in the slides. Then for XA, when we have a variable volume system, so we'll have CA epsilon A plus CAO all over CAO minus CA. Okay, taken from this original formula that we have. So kindly check my what I did with the expansion. So we have CA epsilon AXA, we have CAO and CAO XA. We transfer this one here, we factor out XA. So CA epsilon A plus CAO coming from here. The right side is CAO minus CA. That's it. So we want the XA isolated on the left. So you have XA. Is it the other way around? This one should be here and this one is in the numerator. That's the purpose of checking. Your XA will be the opposite of what I have written originally. So you'll have CAO minus CA all over CA epsilon A plus CAO. Somebody is writing on the chat box. Sulit. Correctly. Yeah, thank you. So sulit siya. So this is our XA and this will be the XA that we'll be using for each of our runs. Okay? For each of our runs, we have 4 runs here and the thing that is varying here is actually the CA. Because in each runs, our CA varies, so our XA varies as well. Your epsilon A and your CAO are the same. Okay, so our CAO is 100 millimole. So can you do that? Can you write down in a piece of paper there your CAO, which is 100 millimole, and your CA, which is varying? I'll just give it as an assignment later. And epsilon A, you write epsilon A, which is negative 0.5. Okay? CAO is 100 millimole and epsilon A is negative 0.5. So I will assign to each one of you each of the runs. I'll just call 4 names. That way you can solve for the XA. So what you need is the CAO, which is 100 millimole, the epsilon A, which is negative 0.5, and the CA based on the run that I will assign to you. Of course, you will be needing this formula. So have the formula written in a piece of paper so you can answer for the XA later, which I will be assigning. Okay, so I'll give you 10 seconds for that. Okay, so hope you're done already. I'll go to our data. So for the first here, for the first run where CA is 85.7, this would be computed by Jericho. The second will be by Josh. The third will be by Via. And the fourth will be by Amit. Okay? Drexel Amit. So kindly give me the XA based on the CA that you are to use based on the run assigned to you. So Jericho, Via, is it Via, Josh, and Amit. Anyways.
50 garong ako, miss.
Sige, so si Josh ang una. So we have here Jericho, Josh, Via, and Drexel. Sige. So this is the formula that you will use for the XA. That way I can write it in here in our table. Okay, can you write on the chat box your answer, please? CaO is 100 millimole. Epsilon A is negative 0.5. This is your formula. Okay. Can I ask for the answer for the XA? Kay Josh, 0.4996. So second si Josh, no? 0.4996. And for Drexel, 0.7995. Then for Via, 0.667. And Jericho, Via, Drexel, Josh, 0.25. Okay, thank you. So you have 0.25. Now we go to the rate. So the rate equation was already given. This is our rate equation class. In the rate equation, you still need the same initial concentration. You need the XA that you solve. You need the volume of the reactor, and you need the molar feed rates. Okay, so I'll just copy again the molar feed rates. That way, you will just need to substitute. I write here the visible. So for V sub O, we have 10, 3, 1.2, and 0.5. Okay, so 10, 3, 1.2, and 5. Let me check. Okay. And your working equation is this. For the rate, CaOXaVO over V. So have a piece of paper for that ready for the rate. That's your formula. And you need the XA and the visible in here. So the first rate will be given to me by, let me check. So there's only 6 of you, so may masulit din. So that would be John Albert for the first rate. The second would be for Patrick Tagle. And the fourth would still be for Bia. And the third would be for Josh. Okay, the first one will be John Albert Villarosa. The second would be Patrick. The third would be Josh. The fourth will be Bia for the RA. Please ano ang B. Okay, the volume is, I missed to give you the volume, 0.1 liter. Volume is 0.1 liter. This is your set of information. Right here, the volume. The volume is 0.1 liter. Second. I'll have 0.25. Your volume is in liter. Your volumetric flow rate is in liter per hour. So your rate should be in millimole per liter per hour. Okay. Millimole per liter per hour. That should be your rate. So your answer here, Josh, John Albert, which one is millimole per liter per hour? The 0.25?
25, miss, ang answer.
0.25, sige. So the next one would be Patrick.
2,500, gali, miss. 25.
Oh, sorry.
Ito.
2,500. Okay. So we have 2,500. Patrick, 1498.8. 1498.8. Then we have Ezra, 400.2.
Alam, miss, ano ang akon? Ang last.
Ang last
Wait
year.
lang, miss, ha? Kaya abi ko ang third ang akon.
Okay, while waiting for Via to get the answer, actually, you can start now working on this too. You take the LN. I'll write here a different color than now. You take the LN. I'll just continue here. Okay.
Miss, excuse, pwede po lang ka pabalik sa working equation.
CAOXA times VO over P. So this is the ln of the rate, and this is the ln of the CE. Can you supply me with the ln of the rates? Okay, we have the answer now. 399.725. Layo-layo sang for napitay sila nga duwa. Oh. Is this correct, Josh? 400.2. Can you recheck? CAOXA VO over V. Is that correct? The third value for the rate? Ito ka-drastic sang pagpanaog, and then it's so close to 399.75. $800.4. Sige. Thank you. So this is 800.4. You do the checking for the rest. Okay, I think this is now more believable. Now we get the LNs here. So I'll have the first LN of the rate here by Jericho. The second would be Amit. The third would be John Albert. The fourth would be Patrick. LN of the rates, this one. Jericho, Amit, John Albert, and Patrick Tagley for the LN of the rates. $7.3. 124. Okay. $7.3124. That's for Amit. And then Patrick is 7.1840. Jericho is 6.685. Naman si John Albert. Oh, John Albert is here. 6.685. Okay, for the last, we have the LN. The LNs of the concentration. So the first one will be computed by Via, the second one by Josh, the third one by Drexel, and the fourth one by Jericho. Okay, first LN will be Bia, second LN will be Josh, third LN is Amit, fourth LN will be Jericho. Bia, 4.4509. Josh, 4.200. It's okay. Then I'll have Drexel and Jericho for the last two. Jericho, 3.5086. Amit, ln of C8, the third C8. ln of 50. Rex, are you there? 3.9120. Okay. So actually, what you just need, what you really needed are these two in your linear regression. That way you can find for the slope and the y-intercept of the line. So you have to input this 4 sets of data and then determine the slope of the best fit line and the y-intercept. Can you do that? I give you 3 minutes for that. Oh, may ara na. Salamat. Please, I think may mga sala sa LNRA. LNRA. Ah, okay. Kinagasi. So, siya. Wait, ha? Wait. ln of RA. Sino ganing una ko sa ln of RA? C. ln of RA is, I forgot.
Jericho, miss.
ln of RA, nasulit ko di ho. Which one is, actually, inilang man ng inyo i-ln. So, diinda ang sala. Can you tell me? $5.9908 ang 3997. Akong sala na type mo ni si lang. 5.9908. Which one? May isa pa oh. Or this one? Oh.
Oh.
Okay, wait ha. 7.824. Okay. Sige. So I think that there is now a trend. It's already descending. Kaya naabi daw wala agad siya trend. So this one is descending. This one is also descending. Okay. So thank you for bringing that up, Jericho. So we're now good to go. Can you do linear regression on these two sets of information and tell me the corresponding n and the slope and the y-intercept? This is our answer last meeting. So our slope is 1.56. Our y-intercept is 0.29. I'd like to label this one as old computation so we can compare. I will not erase this old frame. Okay, so I'll wait. So these are your info for LNs of RA and CA. Okay, here we are. So your y-intercept is negative 9071. And the m is 1 point. Write it here. Okay. Is we check ha. So the p is negative 0.9071 and the n is 1.9563. Okay, if this is our b, negative 0.9071 equal to the ln of k. So your k would be 0.40369. Kindly check. Our previous computation for the k is 1.3461. So very far. This one is just 0.40369. Our n is 1.5671. This one is 1.95. More or less, this is more or less 2. If I will just rounding it off to 2 so that you will have an easy manner of writing the units of the k, then your k will have units liter per millimole, and then we have here per hour because our n is raised to 2. Okay, so if it's millimole per liter squared, if you take out the 1 liter unit and the 1 millimole liter, then it will have millimole per liter per hour as the set units. So your rate equation then is equal to 0.40369 C sub A raised to 2. If I round off to 2, the 1.9563. Do you get it? So very far from our original answer. Even the k is very far. If you miss to take note of the epsilon A, the fractional change in the volume. Do you have any questions? So this is our rate equation. Or if you'd like to write it in equation form as it is stated, it should be dCA dt. So differential equation that is 0.40369 C sub A raised to 2. So that's your rate equation. Any question, class? My time is 1:26. We will continue with this tomorrow. If I'm not mistaken, hopefully I can finish everything in this particular set of slides. I still have sample 3, 4, and 5. I think I have 5 examples here before I'll go to the last concept of the holding time versus the space-time. So do you have any concerns? So tomorrow, if all will be smooth sailing, we'll finish all 3 sample problems by then. I'll stop sharing for now. I'll recheck attendance class today. Ginto Amit.